And so that's why von Neumann algebra people are very interested in non-singular ergodic theory. So it's kind of interesting that von Neumann's examples were like this, and you might ask, what other types are there? Let me start with Dyer's theorem, which was proved in 1959. Non-singular dynamical system. You okay with me writing NSDS for non-singular dynamical system? So Dye showed that, and really you make a partition and then you let T act on the partition, and that gives you some if you have just split the space into two, and you say something has 0 coordinate, 0 if it lies in the first of them and 1 if it lies in the second, then you apply T, and you see if Tx lies in the first or the second, that gives you the second coordinate as 1 or 2, and you keep doing that. And that gives you a basis, just from a single partition like that, that gives you an expression, one-to-one correspondence between x and the infinite strings of zeros and ones. Then it's a matter of showing that the transformation becomes the odometer, and well, you can kind of see that up to orbits that is what happens, but then you've lost all control of the measure. So this is really where Gavin Brown and I started working on ergodic theories. We thought, we know stuff about measures, maybe we can say something about these systems. And in particular, Gavin was an expert on Rees products at that point. So we thought we'd try to use some of our knowledge from harmonic analysis and Rees products to say something about these systems. So the problem then becomes, I have to say that there is still no satisfactory classification of type 3 systems, and it's still one of the sort of major outstanding problems, I think. But one has to have a holy grail at the end of one's research, and this was kind of the thing that Gavin and I set up for ourselves as a vision of what we might do using harmonic analysis. Well, we have got some of the way there, and I kind of want to explain where we are at in the process in the rest of the talk. There is a secondary classification of the type 3s, so the type 3s have not remained completely unclassified. There's something called the Krieger-Araki-Woods ratio set. And I thought, I've given this as a seminar talk a number of times, these kinds of ideas, and I usually don't write the ratio set definition up, but I thought that for today's audience I might honor you with a, and let me do it for a group G which I suppose I'll write as R, if I'm really forced to, R of x, B, mu, T, mu G. If for all epsilon greater than 0, for all A with positive measure, there exists B contained in A with the measure of B also positive, and there exists G in G with G of B also contained in A. Sundari tells me I should be a bit more energetic to stop going to sleep as I'm writing and get lazy, so I'm going to start running from one side of the blackboard to the other. And here's the most important thing. So this was invented by Krieger. So here's the picture of what happens. You give me a set of positive measure. I can find a B contain. That's A. There's B. G maps B onto GB. This all has to happen inside A. And the Radon derivative for that little bit has to be close to R uniformly across the whole of B. So that means within the set A, I can find a small thing where the Radon derivative is A. It's close. And proposition, this is a subgroup. If R equals infinity, then you have to change it to for all M, d mu, compose G, d mu is greater than or equal to M, is greater than M, just so you can see how to modify this if you wanted to have R being infinity. And so so the proposition says that the ratio set is a closed subset. No. Is a subgroup. Of the multiplicative group 1 infinity of R plus. And I really want to say it's closed in 0 infinity. Oh yeah. And so, therefore, I thought I'd leave this as an exercise for the students to prove that. And therefore, and that's called type 2.1, sorry, 3.1. the powers of lambda or else just three elements, 0, 1, infinity. Oh, of course, I've forgotten. Could just be the identity. So these possibilities correspond to, this corresponds to, of course, the type 2 factors where there's an invariant measure. And these are all type 3 factors here, or type 3 systems here. So you can actually realize most of these. Oh, I'm sorry. Let's just worry about it for Z at the moment. I wrote T there, so I'm implicitly saying Z. That's a 1. Oh, that's 3 lambda. For 0. Oh, I forgot to write. Yeah, all right. So those are called 3 lambdas, and these are called 3 zeros. And so Krieger and Kohn, I mean, there was a so they showed that there's a unique 3 lambda orbit equivalence class. In other words, the only possible ones. And of course, what you do is you take mu I of 0 equal to 1 over 1 plus lambda. And you can realize those orbit equivalence classes as an infinite product measure on an infinite product space with a fixed lambda there. And the Radon derivatives look like powers of lambda, pretty much. If you change a 0 to a 1 whenever you change a 0 to a 1 in a sequence, then you get a lambda coming in the Radon derivative. When you do it the other way, you get lambda to the -1 in the Radon derivative. So if you look at that odometer action, you'll change a certain number of zeros to a certain number of 1s, depending on the sequence, and that gives you a power of lambda there. So clearly this guy here has got the powers of lambda to the n in the ratio set. And then I think, there was a big there's a single transformation, which is the orbit equivalence class in 3-1. So I think Kohn got his Fields medal for showing there was a unique type 3-1 factor. And in that case, you can take, you can realize this also with mu I of 0 is equal to A1 or A if I is odd, and B if I is even, with A and B rationally independent. I mean, there are lots of different ways of putting the measure on, but that would be a way of creating the whole of R as the ratio set. And unfortunately, 3 zeros are the rest. Uncountably many different orbit equivalence classes. There are more than the cardinality of the continuum. They can't even be indexed by a Lebesgue space. So it's very bad, the type 3-0 system. All you can say is that Radon derivatives are either 1 or very, very big or very, very small. So let me now talk about Riesz products. And let's go back to the circle group. So you take a trigonometric polynomial that looks like this. You take 1 plus, maybe I'll start with 0 perhaps. Does it matter? No, just start with 1. 1 plus a1 cos of 3t, 1 plus a2 cos of 9t. You multiply all these factors together. Just do it a finite number of times and put Haar measure, Lebesgue measure on the end. And then you take a weak-star limit of this. Riesz showed that there is a unique weak-star limit of this, which is singular with respect to Lebesgue measure. In general, if the sum of the AI squared is equal to infinity, then it's singular with respect to Lebesgue measure. Otherwise, it's absolutely continuous. They're typically supported on Cantor sets and that sort of thing. And in fact, if this is the group of triadic rationals, you can probably work out what you're allowed to put in for K and N there. So I'll call this mu is equivalent to, well, maybe I'll call that G or something or other. Then you can see that these are quasi-invariant. The Radon derivatives look like products of these guys here, with a t plus k on the top, and then without the 3 plus k on the bottom. So there's a trig polynomial on the top and a trig polynomial on the bottom with an extra translation term. They look sufficiently chaotic that they might be able to represent type 3-0 systems and, well, more wild measures on. So in fact, So let's think of expanding every element of the circle out in a triadic expansion, triadic decimal expansion. Then this gives you some quite wild measure, so I'll call that x. Then mu goes to a measure on x, and triadic rational group goes to the finite coordinate changes on x. Maybe I'll call gamma to be the finite coordinate changes on x. So you take the set of all strings of zeros, ones, and twos, you change finitely many coordinates. In fact, what the odometer does is it changes finitely many coordinates, and in fact, every finite coordinate change, the odometer will run through all possible finite coordinate changes, and so the orbits of the finite coordinate change group are the same as the orbits of the odometer, and therefore this system is orbit equivalent to one which has got the odometer acting on x, which is just a finite thing here, just 0, 1, 2, and this is exactly the type of thing that comes out of Dye's theorem. So at this point in 1990 or so, Gavin and I thought we will now try to exploit the Riesz product formalism and describe as many measures on the infinite product space as we can, and perhaps that will give us some insight into the type 3.0 systems. So we introduced something called G measures. Mike Keane had previously done little G measures. We then changed that to big G measures. I'll explain the difference in a moment. So G is going to be a sequence of functions, and for the Riesz products, these are the functions, the product from 1 plus ai cos 3t. Sorry, maybe I'll call them GNs here. So if you take the product of the first n terms like this, then we'll call that GN. What's the property of these functions here that makes Riesz's theorem work, that there's a unique limit? So let me average out the first n coordinates by using the coordinate. So these are the changes in the first coordinates, first n coordinate. Call that mu n. Let me write d mu n equal to Gn. So if I have any quasi-invariant measure, I can create a family of functions which satisfy this. So I want I want 1 over gamma n gamma n equal to 1, and I want Gn of x, gamma x over Gn of x to be Gk of gamma x over Gk of x if n is greater than k and gamma is in gamma k. So that's normalization. And that's compatibility. So provided you have, now for any mu, these functions here are a normalized compatible family. Now let's forget about mu and suppose we have a normalized compatible family and say, how many mu's are there with these? Let's try and start with a family of functions like we did with the Riesz products here and ask, can we find measures with those? So we'll define mu to be a G measure. I managed to answer in this work. So I want to talk about Brightly-Verschig systems. So this is a theorem that Hamachi and I proved, which improves Dye's theorem. When did it come out? 2002, apparently. So I think it's good to write up your theorems early, even if you haven't explained all the terms. So the rest of my lecture will be to explain the terms that are here. So I need to explain a whole lot of terms, and basically the rest of my lecture I'll be explaining to you what is a Brightly-Verschig system, what is a Markov odometer. I've kind of explained uniquely ergodic, but I'll explain how that fits into that context. And well, we kind of know about induced transformations, but I need to explain what they are, what a Markov odometer has got to do with a full odometer. So in a way, this kind of answers some of the questions that Gavin and I had, although we don't very well understand what the orbit equivalence classes of these are. But at least it gives you a model, a working model for each type 3.0 system. So let me first draw a picture of what the odometer looks like when considered as a Brightly-Verschig system. We have a sequence of dots, and between each two dots there are two edges joining them which are labeled 0 and 1.